This session was originally conceptualized as a review of the statistical procedures that are particularly common to quality improvement and learning health system applications. Although there are statistical procedures that are primarily used in these applications, control charting, for example, comes to mind, I don't know of anything that's solely limited to those applications. Moreover, I'm not so sure that a general survey, for example, a survey of the various quasi-experimental methods, might be applied in the absence of randomization, would be particularly helpful outside the context of a specific project. Accordingly, I'm going to do something different, namely to discuss the overall logic behind the statistical methods that you'll typically apply in your practice of learning health systems. That said, if you'd like some of the background for a more traditional treatment of these topics, a good place to start is the Wikipedia entry on quasi-experiments and also the entry on statistical process control. I'll start with a few distinctions. One distinction is the one between QI and learning health systems. For now, suffice it to say the idea of learning health systems was developed after QI, and so has borrowed some of its statistical techniques, modified them where appropriate, and also includes entirely different techniques as well. Moreover, learning health systems shares a similar philosophical orientation as quality improvement. If you like the analogy that LHS is an extension of evidence-based medicine, you can apply that same analogy to quality improvement. Thus, it's not only EVM 2.0, but QI 2.0 as well. Another distinction we'll make will be between practice monitoring, for example, checking that at least 90% of patients have an assessment of pain during a palliative care consultation, and practice improvement. For example, checking whether adding a reminder to an EMR improves the rate at which pain is assessed. Or even better, checking whether adding this reminder actually helps reduce patients' typical levels of pain. In general, monitoring requires different statistical techniques than does practice improvement. Before contrasting the statistical approaches to QI and learning health systems, I'd like to make another distinction, namely between QI and randomized trials. This slide summarizes some similarities and differences along a number of dimensions. We'll begin by looking at the randomized trial column in a bit more detail. There are a number of characteristics of randomized trial that drive the logic of their statistical methods. First, there's an important decision to be made. For example, whether drug A is more efficacious than drug B. Moreover, although meta-analysis can be used to combine information across trials, typically each trial is designed to be sufficient as a standalone entity. In practice, this means the trial will have both a low false positive rate and a low negative rate. That is, it's designed to draw the correct conclusion when the new drug is efficacious and also when it isn't. This requirement drives the power and sample size calculation and what makes sample sizes of so many trials so large. Large trials are costly and time-consuming and should only be considered when the decision is practically important and for which there's true equipoise. Equipoise is often a reasonable deposit for drugs and other healthcare interventions, since it's usually possible to picture a path not only to benefit, but also to harm. The high stakes require the strongest possible inference, thus the requirement for randomization. Moreover, for obvious reasons, regulators are particularly worried about false positive conclusions. For example, it's this worry that underpins lots of thinking about adjustment for multiple comparisons. In other words, a characteristic of randomized trials that isn't necessarily shared by other studies is that the analyst wants to particularly guard against making false claims about efficacy. So to summarize, a typical randomized trial is intended to provide a definitive and self-contained answer to a question about efficacy. For example, to use drug A rather than drug B, rather than additional study. This decision takes place within the context of clinical equipoise. These characteristics ultimately drive study design and statistical analysis. Almost everyone's first exposure to statistics is based on the type of thinking that's applied to randomized trials. And it's easy to wrongly conclude that's the only way to do statistics. In fact, form follows function, and the point of the previous discussion was to illustrate the connection between the goals of randomized trials, their design, and their ultimate analysis. It's also an attempt to inoculate you against the idea that randomized trials are a uniformly better design, and the techniques you'll study in LHS are uniformly inferior. There's no need to apologize for observational quasi-experimental designs. Instead, what's needed is a clear understanding of the strengths and weaknesses of the designs and the circumstances under which each design is appropriate. Here's an example of form-following function in a completely different statistical context. Bayesian statisticians reject the idea that trials are performed in a vacuum, and thus wouldn't design a randomized trial as a self-contained entity. Instead, they would prepare a quantitative summary of previous knowledge about efficacy. Exactly how they do so isn't of interest here, other than to note that it involves a distribution of plausible values rather than a single number. They then combine this previous information with the data from the trial, and thus derive an updated estimate of the distribution of reasonable values of efficacy. This so-called posterior distribution becomes the input to the analysis of the next study, and so forth. Here's a picture of the idea. The data shifts the estimate of efficacy to the right and also makes the data more precise in that the spread of the distribution is reduced. Again, what's critical isn't the details of this introduction of Bayesian statistics, but instead is the idea that when the context of the science changes, so should your approach to statistics. QI statistical methods are derived from a far different context than a randomized trial in medicine. Namely, they're derived from industrial process improvement. Their ultimate frame of reference is systems engineering. In a typical application, the manufacturing process is sketched out in great detail. This is where some of the techniques that John Vey presented come in. And a deep knowledge of this process is used to suggest an improvement. Relative to a healthcare application, industrial processes are simpler. Their input's more controllable, and the analyst is in a position to identify process owners as well as leverage points. Moreover, given a sufficiently deep understanding of the manufacturing processes in question, many of the proposed changes are small and will obviously work. There's no need for a definitive study, and for example, it's perfectly satisfactory to perform a small pre-post assessment to verify that the process change works as intended. This sort of uncontrolled assessment would be inappropriate in a randomized trial context, so would be perceived to lack sufficient rigor. To summarize, when considering QI methods that are intended to assess system change, the context is very different from a randomized trial. Particularly, the decision is small rather than large, and equipoise is lacking. What you're usually doing is demonstrating the obvious, and thus the standard for formal proof is looser. To illustrate the derivation of the QI statistical method, let's consider one of the workhorses, namely the control chart. The usual intention of a control chart is to monitor an existing process, but it can also used to assess the impact of a process change. To create a control chart, time is on the x-axis and samples are taken over time. The output in the manufacturing process is on the y-axis. It's continuously scaled. What is plotted is the mean of the sample. For concreteness, let's suppose a continuously scaled output is the diameter of a catheter. From previous time periods, we can estimate the mean catheter diameter created by the manufacturing process, as well as the standard deviation. This information can also be used to derive the level of variability among the sample means, technically called a standard error rather than a standard deviation, under the assumption that the process is stable. To create the chart, you draw a horizontal line at the process mean, and then draw lines for the mean plus or minus 1 standard deviation, plus or minus 2 standard deviations, plus or minus 3. Then we apply decision rules to the control chart to determine whether the process is out of control. For example, the process might be declared out of control if any observation is more than 3 standard errors from the mean. If 2 out of 3 observations are at least 2 standard errors from the mean, 8 observations in a row on the same side of the mean, and so forth. As drawn, the mean value at the last time point is more than 3 standard errors from the mean, and this would induce an intervention. There are 2 things that are important to understand about these rules. First, that they were derived from observations about what would happen to physical machines as they break. For example, extreme observations can occur when a component of a machine fails. Lots of observations on the same side of the mean can occur when a machine gradually overheats. Second, that the rules are only loosely based on formal statistical analysis. What's true is that if the data are normally distributed, we can predict that 95% of all observations will fall within 2 standard deviations of the mean. However, the decision rules don't take into account that multiple analyses are being performed, in other words, 1 analysis per time point, nor is there usually a formal statistical structure associated with the analysis. Decision rules for a control chart really are pragmatic tools, reflect at least as much engineering thinking as statistical thinking. This usually isn't the type of thinking that's persuasive to reviewers of medical journals because the standard of proof for an industrial QI just isn't as high. All this leads to my first recommendation about how to apply statistics to QI and learning health service projects, namely to identify the standard of proof that will be required. If you want to publish your work as generalizable scientific knowledge, you may need to add one or more control groups, increase sample size, and so forth. If you just want to convince yourself, the standard of proof will be more modest. If you want to convince your peers, the standard of proof will probably be somewhere in between. By analogy with manufacturing, the more that you know about the process in question, the lower will be the standard of proof. As with so many other things, your task involves a trade-off. You want to get an answer that's sufficiently accurate approximation of the truth. You want to do so in a way that economizes on resources. One thing you might try during the study design phase is to write up a sample project report. For example, including your proposed study design, blank analysis tables, a list of strengths and limitations. Show it to the decision makers you need to convince, and ask them if that would be sufficient for them. If nothing else, it will assist you to envision the study design and analysis plan. To make the distinction between QI and learning health, let's start with their similarities. They were derived from the same underlying philosophy. They both have monitoring and process improvement functions, and they both use many of the same statistical techniques. Everyone's understanding of learning health systems is a bit different. This slide summarizes mine, at least as it pertains to some of the ways that it differs from and extends quality improvement. First, although from one perspective a process is a process is a process, healthcare processes are more complicated, often by orders of magnitude, than manufacturing ones. Indeed, the extent to which industrial QI methods can be grafted onto healthcare applications has been an ongoing topic of research and debate. The implications of this increased complexity is that considerable thought is required before applying a standard statistical technique from industrial QI to an application in healthcare. Another crucial difference between industrial QI and learning healthcare is that the latter embeds the patient's voice whenever possible, for example, through the collection of PRO data. In contrast, the emphasis in QI is usually on process rather than on the ultimate customer. Learning healthcare is all about data, and among others, the multiple, often longitudinal uses to which data can be put. QI, in contrast, treats the data in more static fashion. Finally, in learning healthcare, the goal isn't just standardization, which is the primary focus of QI, but also is personalization. For example, to use data to help determine what works best, when, for each individual patient. Once this is tentatively determined, the monitoring function, that is, where we monitor whether the care happens as desired, is similar to QI. However, in contrast to QI, which treats process change as intermittent, learning health also continuously embeds a learning function, whereby tentative decisions about the best course of action are revisited and improved over time based on data. As an exercise, let's assess the extent to which the general background information I presented is helpful. We'll take one of the proposed projects and see what an LHS perspective implies for our study design and ultimate statistical analysis.